Good afternoon, ladies and gentlemen. First of all, I would like to thanks to Professor Christina Gnatenko for organizing this fantastic event and for inviting me here. My thank you very much to Professor Volodymyr Tkachuk also. So thank you very much. It's my great pleasure to be here in this city. Yeah.
Thank you very much for coming, and thank you very much all the team, all the members of the Department for Theoretical Physics for having.
Yes, thank you. And also, as a person from Kiev, I think this is a very good opportunity. I don't know, maybe here is a lot of people from Lviv, yeah? And last time I was in Lviv, I was talking already personally to Christina. It was in end of February 2022. You know what happens in Kiev this time. And your city was really a hub who saved a lot of our families, children, to save their lives, maybe, because this time was really terrible for us. And maybe this is a good opportunity for me to say thank you very much for the whole city, starting from taxi driver and ending maybe for some important professors from the Academy of Sciences who called me, who helped us, and who say thank you very much to the whole city. Yeah. And my talk is a bit title is a bit strange because you may ask why Nobel Prize 2022, not the last one. It was also a bit quantum. Yes. Okay. 2022. My answer is very easy because this is still interesting and important. Yeah. And here is reality real? Okay. So in principle, I'm staying here, and I'm not really sure that you exist. Yeah. So I'm giving for you talk and not really. Okay, let's try to understand what this means. And if we consider statement of a Nobel Prize committee, as usual, this is a little bit formal, but I would consider here three important statements, three important terms: entangled photons, Bell inequalities, and quantum information science. Today, I would like to present to you in some very popular way. This will not be really scientific talk. This will be very popular talk and with some knowledge that you need, maybe something like secondary school, I believe, about Bell inequalities. And I would like to start my presentation not with quantum mechanics, but maybe with 17th century, with Sir Isaac Newton, yeah, who has presented what we today call classical mechanics, or even more classical physics, and even the whole field of physics. Sir Isaac Newton has presented this mechanic. You maybe know this story. So, okay, here is that um, the words, the thinking world, materials body are governed by some equations. You may solve this equation, understand. And this is material body. This is starting from bottle, I don't know, this chair, planets, galaxies. Everything is governed by these equations. And what is very important for us is that after that, for example, you have such a cannon which shooting by ball, and if you understand, for example, at the very, very beginning, what is position of this ball and what is its velocity, this is already an instruction to understand what happens with this ball in next time. So this is like an instruction, yeah? This ball at the initial moment of time has an instruction. So this instruction is coded by x0, y0, just a position, and velocity. This is our artillery guys understand very well because they calculate. So you can understand what happens here next time. A little bit later, French philosopher or scientist, also mathematician, Pierre-Simon Laplace, has extended these concepts to the whole universe. He told that our universe is like a watch mechanisms. Yeah. So this works everything so that this works just a big clock. Yeah. Everything we can understand. So everything is prescripted. There are instructions for everything. And he even told that if exists such an intellect who can calculate So this intellect could understand everything what was before and everything what happens after that. Of course, after that, a lot of people, even in classical physics, were talking that it's impossible to have such an intellect, and this is even there exists mathematician proof for this. But this is very boring work. You don't find that everything is in our work is predetermined. Okay, quantum mechanics likely has destroyed it. And this guy, who is called Laplace demon, is, you see, here is a little bit disappointed. Okay, quantum mechanics. Let's go to quantum mechanics and what happens here. So, Christina was talking today a lot about, and Professor Zhkovsky was talking today about Planck constant. It was 19, yes? 1019 or 1091, I don't remember, 1019. Yeah, exactly on time machine. 25 years later, these two gentlemen, Erwin Schrödinger and Werner Heisenberg, has presented equations for quantum mechanics. So next year, this will be 100 years, exactly 100 years. So we will celebrate. We should celebrate. We should celebrate because first was Werner Heisenberg. I believe it was somewhere in summer. Yeah. And Erwin Schrödinger, this is Christmas time after that. Oh, what shall we do? Continue or? Yeah.
Думаю, що нам потрібно безпека понад усе. Ми мусимо піти в укриття. Дякую. Зустрінемося 5-10 хвилин після закінчення тривоги.
Oh, okay. So we should, yes, we should take a break because
People on the camera right now, and this is what the world needs to know. We have scientific conferences here, and we have to take a break because of an air raid. But we will resume, won't we?
Yes.
It's Ukrainian style. We come back.
Oh, okay. Just to remember you, I told you that all classical physics just before alarm looks like a kind of instruction or manual. Yeah. And according to this guy in 19th century, Pierre-Simon Laplace, the entire universe looks like this. Yeah. So this is just watches, this is just clock mechanism. So, and maybe this guy Laplace demon does not exist. It's impossible to exist even from the point of classical physics. But nevertheless, everything what happens in the future, everything. So this already predetermined. So really what it seeks. And quantum mechanics does not work like this. Yeah. And what we stop that these two guys at the beginning, so first was Werner Heisenberg, and after that, Erwin Schrödinger. It was 1925, first at summer, next at the something near Christmas, I believe. They have presented quantum mechanics, and first their presentation was also that quantum mechanics is a set of rules. So maybe for general public, you have seen in a lot of presentations this strange Greek letter psi, C, yeah? And this is actually wave function. And for the wave function, Schrödinger has written some equation, and equation means that if I know this psi function at the beginning, I know this what happens after that all. Okay, but in half of the year after Schrödinger, this another guy, Max Born, has destroyed everything. He has presented a rule, which is now known as Born rule, yeah? And he told, guys, in quantum mechanics, everything is probabilistic. So we have just probability, no determinism, no this predicted things, so no instructions. In principle, there are recommendations, I would say, sometimes very strong recommendations, but no instruction in quantum physics. Okay, no prescriptions, I would say. Albert Einstein was strongly disagree with all this story. And actually in 1935, he was this time already in the United States, and together in Princeton University, and together with two young at that time scientists, Boris Podolsky and Nathan Rosen, He has presented a work that here he has claimed that quantum mechanics is maybe correct, but incomplete. So something wrong in quantum mechanics. And Einstein didn't believe in these deterministic things, never believed, yeah? And this was started very big discussion in scientific community. This discussion was, but by the way, I want to tell you that one of these authors, Boris Podolsky, there is such a fact, but maybe you don't know that he was working during a year or two in Ukraine, in Kyiv, in the Institute of Physics, in department where I was working. Yeah. So that's what he was head of theoretical physics department in Institute of Physics. I don't know why it happens. Nobody understands. He was maybe invited by Soviet government, but how he has escaped, we don't know. Okay. And this discussion was really long. And what we study from this discussion? Actually, two very basic things, two, I would say, memes from Albert Einstein using technology today. First, God does not play dice with universe. He never believes in this randomness. He never believes that our world is really random. And another story that he told, oh, this spooky action at distance, because what today Professor Zhikovsky talked about all these things with bottles, yeah? It looks like one bottle over another one. Really terrible situation, yeah? Something that looks like it happens faster than speed of light. No sending of information faster than the speed of light, but that time it wasn't clear. This discussion was really hard and in scientific community. And only in 1964, Dr. John Bell, he has presented some formalization, mathematical formalization for this point. And he has proven that really in our quantum mechanics, quantum world, there exists this randomness. And it was for me, when I was presenting you this slide with God does not play dice with universe and spooky action distance, this is not randomly. So for me, this is also because we have two facts. That first, there is randomness, and second, there is something that acts through the distance, yeah? Okay, let's consider arguments. At the moment, I would like to present you in simple words. I will try to do it. Yeah, I don't know if I will be successful, but I will do all the best to present in simple words arguments of John Bell for general public. Okay, let's try to do it at least. Quantum mechanics is really strange things. In quantum mechanics, this is random, but this is not the most strange things. Another very strange situation that is quantum mechanics, you sometimes should choose what to measure, which property you want to measure. Yeah. For example, very well-known example, this is position or velocity. We say momentum in physics. This is just velocity multiplied with mass. Yeah. Position and momentum. So you should, when you want to measure your position, you can never understand where position, you can never understand what is your velocity. And also it contradicts. So when you know your velocity, you never understand your position. The same story I could say with two examples, example. It does not exist in reality. Do not say in this riddle. So because this works only for quantum particles in microscopic world. But I will translate it a little bit for our microscopic reality. Just imagine that you have a token. Okay, token, jeton. Okay, this can be, for example, it has two forms, circle or square. But this can also have two colors, either blue, either red. Yeah. You have a choice. Quantum mechanics say you cannot measure. So this is what we have from quantum mechanics. You cannot measure simultaneously form and color. You do not have such a possibility. What can you do? You can measure either this or this separately. But another story, but you can say me, okay, this is just your stupid theory. You simply don't know how to do it. Can you prove that this really, you cannot do it and that this appears really randomly? Because next statement from here, I say that form, square or circle or color appears when I measure it. Just imagine that we have such a strange box, and in this strange box, I can just this token in this strange box, and I can either to maybe take it and understand what is form or to look at the color. But you understand that they exist both simultaneously, and color and form, yeah? You understand that color and form exist. My statement that for this quantum token, color and form do not exist simultaneously. It appears when you measure it. How to prove it? So now we prove it. In order to prove it, we need another guy, Bob. Yeah? Who will do the same, but with another token. Now you have two tokens in one box. After this, this box is separated. One is going to Alice, another one is going to Bob. So Christina, you're Alice, Mike, you're Bob, okay? At the moment, temporary. And what you can do, you can simultaneously measure different things, either form and form. This is your decision. Either color and color, either form and color, either this or this. There is 4 possibilities. And now this is, I believe, very easy, yeah? So my statement before you have decided to do this measurement, no form, neither color exist. Okay. Now I will do some math theory from general part. I would like to ascribe to form some mathematical values, FA. When this is circle, FA is +1. When this is square, FA is -1. Okay? The same story will be for color. I will only say this CA. This for me just convenient to ascribe some numbers for this. Okay, for Bob I will do the same. So we have 4 values, FA, FB, CA, CB. Each of them can be plus or -1. And we think that before I measure all the stupid things, they exist. Yeah? Okay. This also means that exist such products. For example, FA multiplied by FB, yeah? FA multiplied by CB, CA multiplied by FB, CA multiplied by CB. When each number exists, of course, its product exists, yeah? Nothing difficult. Oh, good. Well, it's not, but this also means maybe you don't see it through the Zoom, yeah? But some other mathematical combination. Something like this. And when you really familiar with school math, you can understand that, okay, something wrong with my pointer. Sorry, pointer doesn't work. Okay. Okay, you can understand that this combination can be only plus or -2. But all of you know school physics, and just imagine. So when I do experiment, so just separate this box and to Christina, another to Mike, you do this experiment. After that, many times, suppose you will always have for this plus or -2, 2 or -2, okay? No other possibility, but you can find mean values. 2 plus 2 divided by 2, this will be 2. 2 minus 2 divided by 2, this will be 0. So you will never have more for mean value of these things, more than, so you can measure more than 2. This means that mean values, so because mean of sum is sum of means, so this means that you can consider such a combination. And this combination with absolute value never exceeds the 2. So this means that this combination, when they combination exist before, this means that these things which we can in principle measure, which we can reconstruct, never exceed the number 2. with absolute values. And you can imagine that even with quantum mechanics, when we can calculate it, it doesn't work. This is more than 2. Okay? And actually, last year, Nobel Prize laureate, Professor Asper, I believe that Professor Clauser was first, Professor Asper, and after that, with Professor Zahlinger confirmed, they have done different experiments. They have done these experiments with optics, with separate photons. Photons have such a property like polarization. This is exactly like color and forms that I told you now. They do it, and you can confirm that this number is 2.83. So this means that in our quantum worlds, reality does not exist. Sorry. Because it appears only when you look at this, but it does not exist locally. Local realism, because this is, you see, we need another guy, Bob, not only Alice, but also Bob. Yeah. So reality really appears when we look at it. This is our interpretation. It was a lot of work because it was so-called loopholes. After that, it was closed loopholes, but it appears a number of interesting theories which told us how can we preserve this determinism, how we can save these rules. So we want to have these rules in our world, yeah, because we want to have determinism. This is very convenient things. So people were living with our humanity, were living with these 300 years, and here is the stupid quantum mechanics. And there are some alternative concepts. I cannot list all of them, but maybe I will tell some really interesting. First of all, this is non-local realism. Non-local realism is really interesting things, but we should sacrifice, in this case, special relativity. Yeah, but I believe price is very strong. By the way, in Poland, when I was student, I was reading papers in physical review by Professor Caban, if I correctly pronounce it, yeah, with very nice idea in this direction, yeah. So in principle, maybe it's also possible. Okay, another such a theory, super determinism. What this means? This is, I would say, such a kind, I call it perfect conspiracy theory. Comparing with all other conspiracy theories, this is nothing. So they are nothing. Yeah. So this is super conspiracy theory, and this conspiracy theory you can never find some arguments contra this conspiracy theory. This means that our world is so strong, determinism so strong, that you have these rules, prescriptions, not only for what you have measured, but also for what you decide to measure, colors or forms. And because our words work so this Bell type experiment should work for many kinds of physical system, for photons, atoms, Josephson junctions in superconductors, and so on. It's really unbelievable how work can be so complicated. Another story, many-word interpretation. Some people believe that when you make some measurement and have some random results, another story does not disappear. Yeah, another result. So it exists. For example, if I do now quantum measurement and result that I obtain that result, for example, 0, I say I go here, and when I get result 1, I make step here. This means that here now staying another me, yeah, he is just here now, yeah, and telling like this, yeah, looks like very strange and exotic theory, but mathematically looks correct, yeah, it can be, yeah, because nobody, but we do not so all this interpretation has one disappointed, so we cannot falsify them. So either they are scientific, this is a good question, you see, because we cannot propose experiment in order to check these theories. They contradict to nothing, but no such experiment. Yeah, in physics exists such things. Okay, what I would like to say in conclusions, I believe that I was interested here in quantum theory, that our world appears to be either non-realistic or non-local, or even both, but we are so pragmatic creatures, I mean people, yeah, that we use it to make new technologies. Even if we are not realistic, we use it to create some new technologies. Thank you very much.